Hi, my name is Usong Choi, and I'd like to introduce you about the paper Simpler is Better, Visual Semantic Segmentation with Classifier Weight Transformer. First, I want to tell you some basics. Few-shot learning is about learning new classes from just a few training examples like 1 or 5 images. Semantic segmentation, on the other hand, means labeling every pixel in an image. When you put these two together, visual semantic segmentation tries to find and segment new object in a query image using just a few labeled support images. Since there is so little data, regular training doesn't work well, so meta-learning comes in. It teaches the model how to quickly adapt and make accurate predictions. Most visual semantic segmentation models are comprised of a CNN encoder, CNN decoder, and a simple classifier, and they train the whole thing with meta-learning to handle new classes well. Basically, the entire model learns from the support images and mask, then tries to segment the query image. But there's a problem. When you have only a few support images, updating the whole model with millions of parameters can easily lead to overfitting and unstable training. To fix this, a new approach came up. Pre-train the encoder and decoder, then freeze them, and just meta-run the simplest component, a classifier. Surprisingly, even this simple method beats the previous best one. However, this naive baseline cannot adapt to each query image because the target object may appear drastically dissimilar to the ones in the superset images. To address this limitation, we introduced the CWT, which stands for Classifier Weight Transformer. CWT adaptively updates the classifier weights based on the characteristics of each query image. Specifically, the CWT follows a standard transformer-style query key-value structure. Through this architecture, the CWT computes a query-specific adapted classifier weight W star using an attention-based mechanism as defined by the following equation. The model compares the initial classifier weight with query features to compare the attention scores, which are used to adjust the weights based on the query image. This allows the classifier to adapt to intra-class variation. The transformer is trained during meta-training and kept fixed during testing, and then adaptively updating the classifier weight for each query image without further learning. Here's how the whole thing works. First, encoder and decoder are pre-trained and freeze. Then, classifier is trained using support images and mask. After that, the query image is passed through a frozen encoder-decoder to extract features. Finally, transformer adjusts the classifier weight based on these query features. This adapted classifier is used for final segmentation. In experiments, they used COCO and Pascal datasets, which are famous datasets for future semantic segmentations. Performance was measured by MIOU, and they considered two cases, 1-shot and 5-shot. The results show that on COCO dataset, their model's score outperformed the previous best in both 1-shot and 5-shot. However, on Pascal dataset, their model performs worse than the previous best in 1-shot, but shows better result in 5-shot. They also tested in cross-domain settings. The results show that the proposed method shows strong generalization ability. In both cases, CWT outperformed the previous best. This suggests that their training method is more effective than a conventional full pipeline meta-learned model. This paper proposes a simpler and more stable approach by freezing the encoder and decoder after pre-training and only meta-learning the classifier. This reduces overfitting and training instability. To adapt to each query image, it introduces a transformer-based approach. It leads to a strong performance on multiple benchmarks, even outperforming certain methods with simpler model architecture. However, the model still struggles when there are large appearance gaps between support and query images, like different viewpoint poses or occlusions. Handling such extreme variations remains a challenge for future work. Thank you for watching my presentation.